So titration is a very common chemistry technique. It's a very good analytical technique that can help you figure out the concentration of a particular substance or ion in a solution where you don't know the concentration. The basic setup is that you're going to use a piece of equipment called a burette, which is a very tall, skinny glass tube that has lots of very precise markings on it. The burette has this tap here, which allows you to add very tiny amounts of solution at a time. And so usually in the burette is going to go what we could call the standard solution, the solution that you know its concentration. So this is generally the one where you know its concentration ahead of time. And then in the flask down below, the solution that is being titrated, you put this down here, and this one you don't know its concentration. You can measure out an exact volume of it, but you don't know the concentration of the substance in question of this solution down here. A couple of things about the setup of a titration is that the burette, the volume markings on a burette are always written in reverse. It's a little bit odd at first. It's done on purpose, but if you see these pictures here, this is what the readings on a burette will look like. So going from 6 milliliters down to 7 milliliters. And so when you read a burette, first of all, you always read from the bottom of the meniscus, which is how we always read volumes. So you want to read from the bottom here, right? And then as you estimate it, so here's 7, that means this is 6.9, 6.8, 6.7, and 6.6. So this thing is between 6.6 and 6.7. So we know for certain, right, if we think about uncertainty, that we should record this value as 6.6. Those two we know for sure. But then that last one you could estimate. If you could really tell that it's past the 6 here, then saying it's 6.63 or 6.65, anything like that is a worthy estimate of that last digit. So the uncertainty on this reading is half of the smallest increment. The smallest increment seems to be 0.1 milliliters, a tenth of a milliliter, and therefore we would want to record these values as plus or minus 0.05, half of 0.1. So the uncertainties are quite small on a burette. It's a very precise instrument. But the point is, don't read this as 7.35, right? Because it's above 7. It's very common to read it backwards, or even to read it as 6 and then count up 3.5. The markings go down. It is a little bit odd. So we'll see if you can do this one on your own, and we can go over this one in class, and you can estimate what that volume would be. So in a titration, the point is that you've got these two solutions that are going to react chemically with each other. You've got one reactant in the flask and one reactant in the burette, and you're going to add the one from the burette very, very slowly until you reach the end point of the reaction. And the end point, usually you're going to know that you've reached the end point because of a color change is the most common way to do a titration. So either the reactants themselves have a certain color, and at the end point they will change color very dramatically, or you add what's called an indicator, which is a separate substance that will change color right when the end point has been reached. So a couple of practical considerations about titration is that when you start off, right, you have the original color, and at the end you're looking for a different color. But the end point, usually the color is very, very faint. You're hoping to perfectly match the two different reactants so that you get a very faint color at the end point. It's very easy to go too far and add too much of the reactant in the burette and get a dark color, and that makes your results less accurate. So since that's so easy, it's so easy to overshoot. What you're normally going to do in a titration is start off by doing a rough trial. That means that you let out the stuff from the burette pretty fast until you get that color change, just to get an estimate of around where the color change is going to happen. That way, on subsequent trials, you can go really fast until you get close to that amount of reactant being added, and then you can go extremely slowly. And your goal is that when you add one drop of this reactant, it should make the color change, and it should then stay that color. So the goal is that one drop, that you can match this equivalence point, this end point, with just one drop of the reactant in the burette and perfectly match the reactant in the flask. So that is your ultimate goal. So usually you're going to do one rough trial and then follow that up with 2 accurate trials. If you have more time, sometimes you do more than 2 accurate trials. The best thing you could do is to keep repeating trials until you get the same volume added time and time again, at least twice in a row. That would be ideal. A careful other consideration is that at the end, when you get really close to the endpoint, the color change, the color fading, may continue to happen, but very, very slowly. So normally, as you add these drops, let's say it's changing from clear to pink, as this one is, the closer you get to the endpoint, the mixture will start to stay pink for a while, but then will slowly fade back to clear. So you have to be patient, and just because it turned pink when you added the drop, you actually have to keep swirling it or stirring it with a stir bar until the color fades away. And so you want to wait for like at least a minute or two at those points to see, is the color going to fade away or is it going to remain in this new color? So we'll remind you of that when you do it in class, but the endpoint can be a little bit tricky to spot because of that slow fading of color. In terms of the actual math, what you're trying to reach is the endpoint, which we also sometimes call the equivalence point or the stoichiometric point. Now, the reason why we call it that is because at this point, at this endpoint, it's when the moles of your reactants are equal, or if not exactly equal, at least equal based on the chemical equation and the mole ratio. So we'll start with one that has a 1-to-1 mole ratio. This is a classic titration between a base, sodium hydroxide, and an acid, hydrochloric acid, with an indicator inside. Now, I'd be adding NaOH that has a known concentration, and you would be having HCl in here that you don't know the concentration of. And the idea is, when you get this thing to change color, that will happen right when the moles of NaOH equal the moles of HCl exactly, based on this 1-to-1 ratio. So I've drawn a little picture here to try to explain that. Think about it as every time you add some NaOH, right? So you start off and you only have HCl in the flask. But as you add NaOH, the NaOHs react with HCls as you add them. So one drop, think of it as taking out one HCl, right, this one, and turning it into an NaCl. Okay, then you add another drop or another milliliter, and now you've got 2 HCls have been taken out. So now you've got 2 NaCls instead. And then you keep adding more, and now you've taken out 3. And finally, all of a sudden, when you've taken out all of the HCls, when there's no more HCl, that causes this very distinct color change to happen from clear to pink. And that's when you know you've reached the endpoint. So at the endpoint, all of the reactant in the flask has been used up, has been reacted. And so then the color change is triggered by the fact that all that HCl is gone. Okay, so we keep on adding more NaOH until we get to that clear color change distinction of the endpoint, and then we'll know that we're done. Now, since we can stop it exactly when that color change happens, we can assume that fairly precisely we have added the exact amount of NaOH we need to use up all of the HCl. And since in this chemical equation, there are no coefficients written in front of these formulas, so that means one of this mixes with one of that, reacts with one of that. That implies that at this point where the color changed, this endpoint or equivalence point, the moles of NaOH and the moles of HCl are equal because it's a 1-to-1 ratio. So I add exactly the right amount of NaOH to perfectly match the moles of HCl that are in the flask, and at that point the moles are equal. In terms of the calculations, the volume that I added, I can calculate by doing volume final and volume initial. This is why actually the burette is numbered the way that it is, because the low numbers are at the top and the high numbers are at the bottom. It makes the subtraction easier. So the volume added, or V1, is the change in volume for the burette, so delta V. We know the concentration of what's in the burette, so if we know both concentration and volume, we can calculate moles, N equals CV. Based on that mole ratio, we said that the moles were equal. The moles of the two solutions have to be balanced based on the equation. So the moles of our standard solution is the same as the moles in the flask. So if I can figure out CV of the burette solution, I know the moles. And now with the moles of the solution in the flask, I can solve for C2 because I know its volume. And that's the goal of the titration, to solve for the unknown concentration.